Hi, I'm Samuel Rabinowitz. I'm a rising senior, double majoring in electrical engineering and computer science, and I'm the co-president of the team.
Hi, I'm Maverick Chung, a rising junior, double majoring in electrical engineering and computer science, and I'm the co-president of the team.
I'm Trevor Fowler, a rising senior studying mechanical engineering with a minor in energy engineering and a certificate in innovation and entrepreneurship. I'm the leader of the mechanical team.
Hi, I'm Muthu Aravoli, a rising junior double majoring in electrical engineering and computer science, and I am the electronics sub-team lead.
Hi, my name is Eric Chang. I'm a rising senior majoring in mechanical engineering and computer science, and I'm a member of the software team.
Hi, I'm Eric Chang. I'm a junior studying electrical and computer engineering, and I'm a member of the computer vision team.
Hi, my name is Sean Gandalia. I'm a rising sophomore majoring in electrical and computer engineering and computer science, and I'm the co-lead of the software sub-team.
Hi, I'm Hyungbin Jun, a rising junior majoring in mechanical engineering with a minor in electrical and computer engineering, and I'm a member of the mechanical team.
Hi, I'm Alan B, and I'm a rising sophomore studying computer science, and I'm currently working on the CS team doing computer vision.
Hi, I'm Christopher Cameron, a rising sophomore double majoring in computer science and statistics, and I'm a member of the computer vision team.
Hi, I'm Kevin Yang, a rising sophomore majoring in electrical engineering and computer science, and I'm a member of the electronics team.
Hi, I'm Rui Chen, a rising sophomore majoring in BME, and I'm a member of the Acoustics team.
Hi, I'm Franklin Wei. I'm a rising sophomore majoring in electrical and computer engineering, and I'm a member of the mechanical team.
Hi, I'm Nick. I'm a sophomore studying ECE and physics. This year, I was computer vision team lead, and in the upcoming year, I will be co-president along with Eric Zhang.
The mechanical team has been busy this year upgrading Cthulhu to Cthulhu 2.0 by improving the frame design to promote passive pitch stability, innovating on all of our actuators, the torpedo launcher, the marker dropper, and the grabber claw, and making more efficient use of the cylindrical space inside the electronics capsule by creating new electronics mounts. One of the major issues with the original Cthulhu was that it pitched forward about 45 degrees when the thrusters were off. We fixed this issue in Cthulhu 2 by creating an entirely new side frame piece that's several inches longer. This enabled us to move the DVL backwards in the design, thus moving back the center of mass of the robot, and we shifted forward the center of volume by incorporating these foam mounts. The foam mounts are also highly adjustable, not only in the positioning of the foam, but also in the number of foam blocks, so that we can accommodate any number and any mass or volume of actuators that we might add to this front area. On Cthulhu 2.0, we also added about an inch to the front mounting area and included only horizontal bars in the design to facilitate mounting. The mechanical team also made an effort this year to better utilize the space inside of our electronics capsule. You'll notice that the mounts shown here excellently utilize the semicircular profile of half a cylinder. There's also space included behind this mount and some others to enable Ethernet and USB cables to be routed between the two halves of the stack. An innovative locking feature was also introduced in our IMU mount, which is also connected to the multiplexer and Arduino Nano mounts. Notice this screw head here that's just flush with the surface of the plastic. There's another screw head that's adjustable underneath the IMU. Those screws protrude through to the other underside of the mount. The nubs of the end of the screw are just barely protruding here. When this is slid in place in the aluminum member that it goes into, those screws can be tightened to fix the entire assembly very firmly in place, so that motion of the IMU relative to the rest of the robot is not a problem for us.
Grabber is positioned on like this. It is controlled by a servo, which goes in here. It is made with 2 water jet aluminum plates with 3D printed spacers to allow this inner jaw to move. There are 3 settings for the jaw to determine the range of motion. This jaw shape was designed so that it would be able to grab multiple different sizes of PVC pipe.
The marker dropper mechanism is reloaded through a U-shaped hole that allows markers to be placed inside and inspected before competition. The hole is then covered with a plate that's secured using a screw. This design ensures that the marker dropper is both easy to load and secure once sealed and installed onto the robot. The entire marker dropper mechanism is mounted next to the downwards facing camera, which reduces parallax error.
Our new marker dropper has a rotating mechanism to release metal balls, which allows it to load multiple markers. Controlled by a single servo, the cross-shaped part in the middle rotates to push preloaded markers to the output tube one at a time. Using a vertical circular structure minimized the footprint of the assembly, allowing for easier mounting. Long output tube in the bottom improved the accuracy.
This year, we also updated and refined our torpedo mechanism from its original design last year. With our previous design, our launcher used two curved arms to keep the torpedo in place before launch, which were quite fragile and prone to breaking. Due to the shape of the arms, they would also occasionally either jam or release early, causing the torpedo to misfire at undesirable times. To fix the issue, we adopted a new mechanism that, rather than relying on circular rotation like the previous design, used a simple linear mechanism, thereby reducing the chances of misfire due to inconvenient angling of the arms. We also refined the design in a more general way by adding various improvements such as eliminating overhangs and excess material to hasten the printing speed and therefore the prototyping and design process.
The electronics team is responsible for design, construction, and testing of the electronics stack, which houses all of our electrical devices and components that have functions such as power distribution and signal processing. We also maintain our computer system, write code to interface with sensors, and in general write any code that is not hardware agnostic. We've had a great deal of progress this past year, ranging from upgrading our computer to developing new custom boards and acoustics algorithms. We upgraded our computer this year to a brand new Jetson TX2. The powerful onboard GPU provides enough computing power to use our new computer vision algorithms. Due to the Jetson using an ARM processor, a more power and space efficient processor than our previous x86 processors, we were able to solve issues from thermal management, with us only needing to use a passive heatsink. We were also able to fit new components in our stack, such as an Arduino and a USB hub, due to the space saved. However, we did encounter a problem with having way too many Docker images, since we now had to publish images for each separate architecture. We solved this by creating our own custom automated build system, as shown on the right. And this allows us to have more fast and reproducible builds that automatically update without requiring any additional input from team members. We have also replaced our main hardware controller for the robot. We used to have the commonly used PICSOC for our controller and used Mavlink to communicate with our ground control station during tethered runs. Unfortunately, this connection would oftentimes drop, causing many delays during testing. By switching over to an Arduino and multiplexer for low-level controls and having ROS established communication, we found that this provided us with a more reliable connection. We're also able to do more complex maneuvers now, such as rolls, and are able to get more information about the thruster's output, allowing us to more easily debug and identify problems when they arise.
For new sensors, the VectorNav VN100 replaces the currently used PixHawk. The VectorNav IMU, which uses a quaternion-based Kalman filter, provides much more accurate data than the PixHawk. This data is then published to a ROS node and processed by the robot. The Blue Robotics Bar 30 is also added, allowing the robot to detect its exact Z position in the water. For other physical devices, new PCBs will also be added to the robot. The ESC PCB will allow a single voltage rail to power all of the robot's ESCs. The Acoustics PCB puts all of the robot's acoustics filters together in a single location.
Finding the location of the acoustic pinger is important due to the number of points offered. Because of the low signal-to-noise ratio, we developed two systems for this task. The first system uses phase difference and time difference of arrival, or TDOA, to precisely localize the pinger. Acoustic signals are sampled from a hydrophone array, and short-time Fourier transforms are applied to generate a list of phases and magnitudes. Based on these magnitudes and phases, a small window is determined. After averaging the phases in the window, the phase differences between the hydrophone channels are calculated and used in TDOA. The graph shows the test results of this system using data collected in a pool, with the gray lines representing the predicted locations of the pinger, and the blue point representing the actual location. Although accurate, this system is susceptible to noise. A second system that is more robust but less accurate was designed to estimate the location of the pinger and provided an initial guess to solve the nonlinear equations of TDOA. In this second system, a separate hydrophone array with a large distance between each hydrophone is used to find time difference rather than phase difference. This is done by first filtering with a Butterworth bandpass filter, then cross-correlating between channels. Using the time differences, the estimated octant in which the hydrophone is located in is determined. This system was successfully tested on simulated data generated in MATLAB.
In terms of our strategy for software, we springboarded off our transition to ROS and Docker to continue with our themes of extensibility and modularity by building standalone code packages that allow for parallel development. Also, having in-house code means that we have more customizability, such as our machine learning for computer vision. Keeping all this together is a lot of frequent communication between subteams and also lots of testing in the pool starting in early autumn. But now that we've had to move virtual, we've actually started using our in-house physics simulation to do lots of virtual testing remotely.
We chose to remove the PixHawk flight controller that we used last year because it limited our ability to customize our controls algorithm and thruster placements. So we designed our own controls package, which determines the power to send to each thruster. It uses the ROS PID package and was designed to be completely robot agnostic. This means that it works for any possible number or configuration of thrusters, so we don't have to redesign it for future robots.
With more advanced control, vision, and overall capabilities for competition, we designed a task planner for our 2020 competition entry to easily and intuitively control our robot's autonomous progression of tasks at a higher, more abstracted level. The task planner listens to data from vision and sensor fusion and publishes instructions for controls and actuators. The concept of our design is to build on top of straightforward tasks, such as movement, to build more complex sequences for the robot to follow, such as leader-follower, and ultimately the tasks required for competition, the gate, the buoys, the octagon, etc. Our task planner is designed such that we can quickly and easily begin our robot's autonomous navigation through the competition course while being able to make flexible adjustments at competition with ease.
To create a realistic underwater simulation, we used Utilization, which is a physics simulator that allows us to load in a model of our robot and apply forces, such as drag and buoyancy forces. The simulation is able to receive thruster power values and to send mock IMU data through ROS to imitate the actual robot, allowing for testing with the rest of the software stack, particularly controls and task planning. Additionally, we calculate bounding boxes on objects within the robot's frame of view, allowing us to mimic computer vision for further integration with the rest of the codebase. When the pandemic forced Duke to close campus, the simulation became especially important to how the CS team tested. Here, the robot is moving through the starting gate and resurfacing after. The view in the upper right-hand corner shows the perspective of the camera on the front of the robot.
For computer vision this year, we decided to completely revamp our old conventional techniques and move on to machine learning, and we're super excited to show you the scalable models that we've built.
To implement machine learning, we used a faster RCNN network with ResNet 50 as a base. The pipeline goes like this. You get in an image, and then we extract the features of the image using a ResNet 50, and then we propose bounding boxes for where the stuff might be, and finally, we use the base ResNet 50 model to classify what's in those boxes and to therefore determine what's there. We started with the pre-trained model, and then we applied transfer learning to our network using the competition footage that we gathered last year.
With the footage that we had from previous competitions, we first manually labeled them and then developed a pipeline to basically read in these images, apply data augmentation such as random horizontal flip and saturation, and ultimately train these. And with that, we were able to train pretty strong models for gate detection and buoy detection, and we now also have the flexibility to do so for future tasks.
In order to test these models, we built a ROS publisher that simulates stereo footage, and we achieved a 95% classification accuracy, as well as a high IOU. And as such, we are confident that our model would scale well for any image classification tasks.